a new map that updates m at x1 with v. I apply that map to x2 that's not equal to x1, and I'll get the same thing that m would have returned on x2. All right, so these three lemmas form the signature of the interface to maps. These are the essential properties of maps, and really almost any representation of maps that should satisfy these three lemmas, and any representation of maps that satisfies these three lemmas will do the job for us. Except there's one more thing we might want, and that is if two maps return the same values at corresponding identifiers everywhere, then they're the same map. And I could have two different binary search trees that have different representations but behave the same. So whether we demand this kind of behavioral equality is a good question. All right, so here's a lemma you should be able to prove just, I think, from the properties above. Let's see what it says. No, you can't prove it just from the properties above because it's about equality of maps. So let's see what it says first. I update m at x with v1. I update the resulting map at x with v2. And that should be equal to the map I get by updating m directly at x with v2. Now, why do I think that's not provable from just the properties above? Well, I could make a different representation of maps, let's say by binary search trees, that satisfies the property above, but, or how about this? Binary search trees are too complicated. How about association lists without elimination of duplicates? So I'll update by just sticking the mapping, the pair xv1, right on the front of the list. So now, on the left-hand side of this equality, we will have two different bindings for x, but v2 will be first. And on the right, we'll just have one. So therefore, this needs to be proved from the intentional, that's intentional with an S in there, the representation of maps. And we will need in this the axiom of extensionality, which is to say, if to prove that two functions are equal, you say for every argument they give the same result. Okay. Reflect. Have you seen reflect before? Yeah. So this is a reflection lemma about string equality testing, this Boolean string equality testing. It'll be quite useful in doing proofs that use maps, and so it's worth proving. Now, here's another exercise. Take some map M, update it at x with the value you get by applying m to x. Well, all right, so at x this returns m of x, but at any other y it returns m of y. So that should be the same as m, really. Again, you'll need extensionality to prove that. Okay, here's another exercise. Take m, update it at x with value v2, excuse me, x2 with v2, update it x1 with v1, and that's equal to m updated at x1 with v1, and then updated x2 with v2, provided that x1 and x2 are different identifiers. All right. Now, sometimes we want actually finite maps. We don't want a default value. We want to be able to test whether a variable is in the domain of the map, and only then do we want to apply the partial function, right? We want a partial function. Now, coq is a logic of total functions. The only functions you get in coq are total functions. You can't have partial functions. But what you can have instead are functions into the option type. So we'll represent in coq partial functions from type A to type B as really functions from A to option B. And therefore, a partial map from string to A is just a total map on option A. And guess what the default value is? It's none. And from that, everything's pretty straightforward. The empty value, the empty map maps everything to none, and it's just defined by the total map empty applied to none. When we update map M at X with value V, we're adding something to the partial map if that wasn't in the domain before, or replacing it if it was in the domain. And so that's just the total map update with sum of V. Okay, and we'll have similar notation for partial maps. It has a double brace in it instead of a single brace. Otherwise, the notation there works the same. There's the signature of sort of the proof theory of partial maps, right? That the empty partial map applied to any string is none. That if I update M at X with V and then look up X, I get sum V. If I update M at X2 with V and look up X1 that's different, I get the same thing that M would have given on X1. If I update twice M, I get an equivalent map, or in this case an equal map, to as if I just updated the second time. That if I update M at X with the value that was already in there, I get an equal map, right? This is the, and then swapping the order of updates for different variables doesn't matter. All right, so today I'm going to use this theory of maps in operational semantics. Later this week, when I talk about verified functional algorithms, I'll use this theory of maps as the correctness specification for binary search trees. That the binary search trees are supposed to accomplish for us implementing key value stores, lookup functions, and what are the properties a key value store should have if you put the key in there binding to a certain value, and then you look it up again, what should happen? This theory of maps describes what should have happened. All right, now that was chapter maps.v in the LF volume of Software Foundations, and now we will turn to the IMP chapter of that volume. IMP standing for imperative. We're going to do the operational semantics of a very simple imperative programming language. So, our very simple imperative programming language has commands. Here's the assignment statement. This is actually notation in coq that stands for sort of abstract syntax trees of programs. We'll have assignment statements. We'll have while loops. We will have simple arithmetic expressions with multiplication and subtraction and integer literals, or natural number literals really, and variables. And we'll have simple Boolean expressions like arithmetic equality tests and Boolean negation. And we'll have if statements, although that's not shown here. Okay, so here's a familiar mathematical function written in IMP. What is this function? Factorial. Sure looks like factorial. Keep multiplying by smaller numbers until we get to 0. Right. Okay. If it's factorial, then we should be able to define the semantics of this programming language and prove that it's factorial. Okay. So, in functional programming languages such as ML and Haskell, and in coq, you have inductive data types that make it very convenient to describe the abstract syntax of programming languages. So here we have abstract syntax constructors for the type AX of arithmetic expressions. And we'll have these four constructors: a num for natural number literals, a plus, which takes two sub-expressions and returns an expression for addition, a minus, and a mult. We'll have a type for Boolean expressions with these, 6 constructors for Boolean true, Boolean false, the test of two arithmetic expressions for equality, the test for two arithmetic expressions for less than or equal, the negation of a Boolean, and the Boolean AND. Remark: when you're designing the abstract syntax of your programming language, don't do it this way. Okay? In general, this looks like it's attempting to manage the type checking of expressions by the design of the abstract syntax. And that doesn't scale very well. It often works better just to have a single abstract syntax type with a bunch of constructors and have a type system for your programming language that decides what's well typed. Okay, this pair of inductive types could be described by this grammar in Bacchus-Naur form. Bacchus-Naur form was invented approximately 1960 for the description of the ALGOL programming language, and it used the theory of context-free grammars, which was by Chomsky approximately 1958 or something. And we're very familiar with it now. But notice how well the theory of context-free grammars can be represented by abstract syntax trees as inductive constructors. When you write down a grammar, you might worry about whether it's ambiguous. But when you write down constructors for abstract syntax trees, or when you write down a grammar for abstract syntax, you don't need to worry about whether it's ambiguous. It's the parser's problem, whether your source language is ambiguous. And you do what you need to in the parsing grammar to deal with that. And the parser produces abstract syntax trees, and then you can apply your semantics to the abstract syntax trees. So that's what we do here. We separate those concerns. This grammar is highly ambiguous, but these expressions made with AX and BX aren't ambiguous at all. We can traverse them because they're trees, they're not strings. Okay, so we can write a program that evaluates arithmetic expressions. So it's a recursive function, fixed point, a-eval. If it's a recursive function in coq, it must be structurally recursive. So that means all the recursive calls of a-eval must be on immediate children of the structure of what we pattern matched on right here that was the argument to this call to a-eval. And clearly that's true here. So let's see what happens here. Another way of telling that that's true here, what am I missing? Oh, yes. Is that going to work? No. Am I in the wrong place? I'm in the wrong place. All right, that's better. Here's how we can tell it's structurally recursive, because coq didn't complain here. All right, so here's our test a-eval. We do a-eval of a plus of num2 with num2, and that should compute to 4. And it does compute to 4, so no problem there. Here we have the function that evaluates Boolean expressions. So it's recursive, but notice that when it gets here to the test of equality of two arithmetic expressions, it calls a-eval to evaluate the arithmetic expressions. So very straightforward. I guess we'll do quizzes. We have a digital device for indicating your answers to the quiz questions, so long as there are no more than 5 choices. You hold up a certain number of digits. Okay, so everybody hold up your hand with some number of digits showing what does this evaluate to. What do I think it evaluates to? 3 plus 4 minus 1. Okay, right. These digital answer indicators work so well, and they're useful for so many other purposes as well, just like your smartphone. Okay, so what we showed here was these evaluation functions. Evaluation functions written like this are more characteristic in some sense of denotational semantics than operational semantics, but that's all right. When we have the semantic definition of the expressions of our programming language, we can use it for things. So what we'll use it for, here we define an optimization program, optimize 0 plus. This is going to take an arithmetic expression and look within it for places where you're doing an add of 0 and simplify the expression to get rid of the plus 0. So it's going to take an input expression, it's going to return an output expression. So how does it work? Well, if we just find some number, we'll leave that expression alone. We'll return the expression that it was given. If we find 0 plus something, then we'll recursively optimize to something, but then we'll throw away the 0 plus. And when we find E1 plus E2, we will recursively optimize in E1 and in E2. Now, we could do better than this, because what if this returns a 0? Then we're leaving a 0 in the result. So optimize 0 plus doesn't optimize as aggressively as it could, but it ought to work. Now, what does it mean that it ought to work? It ought to return an expression that's equivalent, that evaluates the same. So let's try it. Here's our expression. 2 plus quantity 0 plus quantity 0 plus 1. And that, optimize 0 plus of that, equals the expression 2 plus 1. And that's proved here by reflexivity. And here's the theorem. It works. What does it mean that it works? It doesn't mean that it removes every 0 from your expression. It means that your expression is equivalent. And what does equivalent mean? It means on any expression A, optimize 0 plus, the evaluation of the optimized expression is equal to the evaluation of the unoptimized expression. That's our theorem. And how do we prove it? Well, by induction. By now you must have figured out that the way you prove it is by induction, whatever it might be. We'll do induction on, well, when you do induction, it has to be induction on something that's above the line. That narrows it down quite a bit here. Okay, so we'll do induction on A. We have 4 cases because there are 4 kinds of constructors in this expression type. And if we were to simplify optimize 0 plus of num n, we would get num n. That's why reflexivity proves this one. In this case here, we could simplify. Let's simplify. All right, that didn't make it simpler, did it? But we can get a hint about what to do next, right? Below the line, on the left, we have a pattern match on A1. So it does different things depending on the form of A1. So in the proof, we could destruct A1 and try it by case analysis.